Hello, this video outlines the procedure for using partial fraction decomposition. Partial fraction decomposition is a method that is used most often in calculus when integrating tough fractions, but it's useful for a lot of different things in algebra as well. And this particular lesson introduces it algebra style for students who are in maybe Algebra 3 pre-calculus or Advanced Algebra and Trig, depending on where you are and what kind of school you're enrolled in. So, my name is Melody Elrod, and I'm a private tutor based in Middle Tennessee who also does online tutoring. This video is purely informational. There's obviously no charge or anything. If you find it helpful, feel free to visit www.melodyelrod.com for more information about me and even a video on how online tutoring works. But for now, let's get to business here. So let's start. Partial fraction decomposition is the taking apart of larger fractions. Fractions kind of like this one, where you've got one big fraction. What I really want to do is be able to take it apart and put it into two smaller fractions, kind of like these guys here. Now, let's start by making sure that we know how to put the fractions together into one big fraction before we try to decompose them into two simpler fractions. So to add two fractions, such as these, we generally need a common denominator because we know that to add or subtract fractions, we need a common denominator, and it's no different for rational expressions. The common denominator in this case would be x plus 4 times x minus 3. So in order to gain a common denominator, we make sure that we multiply by x minus 3 over x minus 3 for this first fraction, and then for the second, x plus 4 over x plus 4. Okay, once we have multiplied them together, we've achieved our common denominator of x minus 3 times x plus 4. And on the top, if we multiply some things out, x times x and negative 3 times x gives us x squared minus 3x. And 2 times x and 2 times 4 gives us 2x plus 8. So simplifying these fractions, the numerator of this fraction would give us x squared minus x plus 8 all over our common denominator, x minus 3 times x plus 4. Now, I get a lot of questions about whether we should simplify by factoring, should we simplify by distributing, and honestly, your answer there is what is simplest really depends on your goal. What is your objective? Our objective in this particular problem was simply to add these two fractions. So in simplest form, we do want to make sure that we can reduce the fraction to its lowest form, to its simplest form, and to that end, we might try to factor the numerator x squared minus x plus 8, but there's no two numbers that are going to multiply to be positive 8 while adding up to be negative 1. So this does not factor, and so that leaves us really with no reason to multiply out the bottom either, so here's our final answer. Now that we know how to add those fractions, which means we could also subtract those fractions, let's talk about what we would do to decompose a fraction that's already been put together this way. Well, more than likely, this particular fraction came from something over x plus 2 plus something over x minus 3. So the first rule of partial fraction decomposition, if there are such things, I don't really like to think about rules, but the first general tool in your toolkit, if you will, is to factor the denominator. Now, this particular denominator is already factored, which is great. I had to think there for a second how to spell denominator, and I think I got it. Anyway, never said I was good at spelling. So, but this particular denominator is already factored for us, and so what that does is it tells us that x plus 2 is one of our denominators, and x minus 3 is the other. But the tricky part is figuring out what goes in the numerator. We want proper fractions. So there's our second general guideline, our general tool, is that we seek proper fractions. Okay, well, what is a proper fraction? And apparently I can't spell fraction either. That's just sad. Anyway, so a proper fraction, as opposed to an improper fraction, is a fraction where the denominator is of lesser degree than the numerator. So a proper fraction, if we have a first degree denominator, will leave us with a 0 degree or simply constant numerator. And since our numerators don't necessarily have to be the same, we give ourselves two different new variables to stand for the constants that will eventually be our numerator. So these two numbers here represent constant values. And remember that a constant is simply a number, an additive like 4 or 7 or 52. Okay, those are all just constants. Or honestly, pi is a constant. You know, negative square root of 3 is a constant, all those things. Okay, so the next thing that we want to do is we want to eliminate the denominators in this equation up here. So we want to multiply by that least common denominator to make this particular equation all on one line. I'm not going to call it linear, but all on one line, no denominators. And that is going to yield this. So that means that we'll have x plus 7 on the left-hand side because we multiplied by x plus 2, x minus 3, right? And that canceled all this stuff. And then here, if I multiply by x plus 2, x minus 3, same thing here, x plus 2, x minus 3. What that's going to do is it's going to cancel off these guys, and it's going to cancel off these guys. And I'm going to be left with x minus 3 times a and b times x plus 2. Now, for really simple problems like this one, because this actually is a very simple problem, there's a really neat thing that we can do. And that is that we can use convenient x values to find a and b. And what do I mean by convenient x values? Well, convenient x values are values that would make these factors in here, this this x minus 3, this x plus 2, that would make those 0. So convenient factors for this particular, convenient x values for this particular equation would be x is 3 and x is negative 2 in this particular problem. So let's try that. Let's put in let's see here. Let's put in 3. Okay, so for x equal 3, this is what happens. We get 3 plus 7, is equal to 3 minus 3 times a plus b times 3 plus 2. Okay. All right, so on the left-hand side, I have 10. And on the right-hand side, I have no a's and I have 5 b's, which since there are no a's, that means that b must be 2. Okay, that was actually quite convenient because it made the a go right away. In fact, I didn't learn it this way when I learned partial fraction decomposition for the first time. I learned it a more complex way that will work for a more widespread number of cases, quite frankly. And we will look at that in the next example. Okay, so for x equal negative 2, we get negative 2 plus 7 is equal to, negative 2 minus 3 times a plus b times negative 2 plus 2. Okay, negative 2 plus 7 is 5. Negative 2 minus 3 is negative 5a. And b is multiplied by 0. So again, since we have no b's, a is simply negative 1. And so what that gives us is this. It tells us that x plus 7 divided by x minus 3, x plus 2 decomposes into a over I believe x plus 2. Let me double check myself. Let's go back up there and make sure I've got them in the right order. Because I did pair A with x plus 2 and B with x minus 3, so it is important that I put them in the correct order now. And 2 over x minus 3. So this is the decomposition. Now we can double check ourselves and make sure that that's true. Okay, so if we wanted to add them back together, okay, so I'll do that in a different color. If we wanted to add them back together, we would simply say that we wanted to do negative 1 times x minus 3 over x plus 2 times x minus 3, and 2 times x plus 2 over x minus 3 times x plus 2. Okay, and when we gather that together, we've got negative x plus 3 plus 2x plus 4 all over x plus 2, x minus 3, and that gives us x plus 7 over that common denominator of x plus 2, x minus 3. So it worked. Excellent. So our decomposition does indeed give us the correct answer. Now there is more than one decomposition to be had for every pair of fractions. If you use the same method on every pair of fractions or every rational expression, you will probably get different kinds of answers. But there really should only be one, excuse me, but there can really be multiple answers for the same problem. All right, so let's move on to a slightly more complex problem. Because not all problems are going to give you such nice, sweet little answers. Let's consider this guy. First of all, the first rule, remember, of decomposition was that we need to factor the denominator to see what's happening here. So let's do that. This factors into x times x squared plus 4. And x squared plus 4, though it looks a lot like a difference of two squares, is actually the sum of two squares, and so therefore does not factor any further. So there it is. Now, if we want to decompose this, what we really want to do is we want to be able to, and I'm just going to move this over. I'm just going to call this our new problem so that we can see what we're doing on the screen. So what we want to do is we want to create some fraction over x and something else over x squared plus 4. Well, we know that we're seeking proper fractions, so the rational expression that has an x in the denominator will have just a constant term in the numerator. For the second fraction, however, this is not linear, it's quadratic. And so a quadratic denominator should be paired with a linear numerator. So there's another rule. And how many rules do we have so far? Let's see, that was just in case you're taking notes, right? So that was 4 rules so far. So we'll go back and talk about our 5th rule, which is that for a quadratic, right, x squared kind of denominator, we need a linear ax plus b kind of numerator. Now, you'll notice that I put a here and bx plus c here. That is because for every single term in the numerator, I have to have either a constant or a coefficient. So again, these letters, this a, this b, and this c, all indicate constant values. Okay? Now, and again, you can use different symbols, different variables, whatever, for those constant values. I tend to use capital letters from the beginning of the alphabet rather than lowercase letters from the end of the alphabet, just simply so I don't get confused with what really is the variable here. But you may see it done different ways. I think most books probably do it this way. Okay, so we follow that same rule again. We multiply through by the common denominator, and we get 3x squared plus 4x plus 4 is equal to a times x squared plus 4 and bx plus c times x. Now, this time, we're not really going to have a convenient x value that we can try. I mean, I guess we could plug 0 in maybe and get some things to work out. We could figure out what 4 is set equal to, but it's actually just going to end up that, well, we can figure out what A is probably, but it's going to be harder to find out B and C. So this one doesn't have as many convenient x values. So when we can't find convenient x values, then we distribute and find the common terms. And let's talk about what that means. So let's multiply out this right-hand side over here. So I've got ax squared and 4a. I've got bx squared and cx, which means that if I put them in order, I've got ax squared and bx squared and cx and 4a, because remember 4 and a are both just numbers. All right, and that's set equal to this 3x squared plus 4x plus 4 over here. Well, I can start to match some things up if I simply group. My x squared term can be pulled out of this a plus b, this a and b terms here. Then we've got cx, and we've got 4a. So let's talk about what that does. This actually makes something really interesting happen. A plus b has got to be our 3 coefficient, or excuse me, our x squared coefficient, which happens to be 3 over here. So this tells me that a and b together are 3. Okay, we also have the cx term and the 4x term, which tells me that c is 4. Well, that was very convenient because they just told me what c is. That's beautiful. They also have 4a and 4. So we know that 4 is 4a, which is also pretty simple. Means a is 1. So now all I really have to do is plug that 1 in back over here and pick up the rest of this equation. So b is 2. And that's nice. What I have now is the tops of my fractions are going to be a and bx plus c. So let's talk about what that looks like. All right. We've got this. We're cooking now. All right, so we've got 1 goes over our first fraction, which was x, and bx plus c, or 2x plus 4, goes over our second fraction, which was x squared plus 4. So now we know that 3x squared plus 4x plus 4 divided by x times x squared plus 4 is the same thing as saying 1 over x plus 2x plus 4 over x squared plus 4. And you can double check that. You can check my math and verify that I've gotten that correct. Let's see here. So we'd have x squared plus 4 and 2x squared. Yep. Plus 4x. Yeah. So we've got it. We've got it. Okay. Good. So so this is our partial fraction decomposition for a more complex denominator. So let's review just real quick what our rules are. Okay, so we know that first of all we need to factor the denominator. We are seeking out a proper fraction, so whatever you put in the denominator, you need 1 degree less in the numerator. Number 3, we need to multiply by the least common denominator to find some equation so that we can begin to solve. Our first tool in the toolbox for solving this is to use convenient x values to find your a and b or your c and d, whatever you've got there. But then we also know that for a quadratic, we end up putting up a linear numerator, meaning that sometimes if we can't find convenient x values, then we just go ahead and distribute out and find those common terms. Those common terms will set up for us a set of equations that more than likely will be pretty easy to solve. They're not always this easy to solve. Sometimes we have to do a little bit more work. We have to work a set of linear equations or something. Okay, let's look at one more possibility though. What if we're set with this example? This is not a proper fraction. And partial fraction decomposition on something that is not a proper fraction doesn't really work all that well. First of all, I can't factor the bottom of this. And if I did, it wouldn't give me a sum that would end up giving me cubics and squares and all that kind of stuff. So this next one, I think we're on maybe step 7 here. Let's double check ourselves. We're on, yeah, step 7. That is that if you start when starting with an improper fraction, divide first. Now, I'm not going to go through polynomial long division here. You can actually find an example of that on my channel, on my Melody Educate channel on YouTube. I believe it's one of my first videos, actually. It's me writing on paper instead of on the computer software. So it is actually a pretty old video, but talking about long division. Okay, so this is using polynomial long division. Or if you're just dividing by a linear factor, you can use synthetic division. Okay, and then you go through the rest of the information. If you have a fraction left over that requires partial fraction decomposition as your remainder, well, then it's easy enough to do partial fraction decomposition as we've discussed. So that's the end of it. That's where, as far as I'm going to take it for now. Again, my name is Melody Elrod, and if you have found the information that you've seen here helpful to you, then I encourage you to visit my website, melodyelrod.com, or visit my channel on YouTube, which is Melody Educate, all one word, and see if there's some other things here that you might find helpful. I hope you have a great day.